Session 12, New Cryptographic Primitives II. And our first talk will be a work-in-progress talk titled Rec Proofs, Merkel Trees with Updatable Batch Proofs and Their Applications. Talk's being given by Babis Papamanthu, who has two affiliations, one with Lagrange Labs and the other with Yale University. Okay.
All right. Hello, everybody. My name is Babis Papamanthu. I'm faculty at Yale University, and I'm also serving as chief scientist at Lagrange Labs, where I'm spending my sabbatical this year. And today, I'm going to talk to you about some of the work that I've been doing at Lagrange Labs on Merkel trees with updatable batch proofs and their applications. So if you love Merkel trees and you love snarks, please stick around. I'm really hoping you learn something from my talk. Okay? Great. So let's start with the basics. What is a Merkel tree? I don't have to convince you about the applications of Merkel trees in the blockchain space. Merkel Patricia tree, for example, that is used in Ethereum, is a type of Merkel tree. But let us review it here. I'm going to present like a basic version of Merkel tree. It's a way to commit to a set of elements. Say you have like 16 elements here. And the way to commit is to start building a recursive hash structure. So you compute this hash at the first level, then you compute this hash at the second level, and you continue, and you end up with what we call a root of the Merkel tree. That is a commitment to the leaves of this tree. Okay? Why this is useful? Well, if you trust the commitment, you can provide proofs for any element in the set. For example, here I'm going to show you how to provide a proof for element A5. You just give the hashes along the path from the element to the root. Okay? And now how do you verify this proof? You just recompute the hash structure until you end up with the root. And if the root matches, you're convinced that the element that you started with, in particular in this example A5, is indeed a member of the set. Okay? I'm hoping most of the people in the audience know about this. In case you don't, that's what a Merkel membership proof is. Okay. What I want to talk about, which is a focus of my talk here, is about updates. Now, what if an element in this Merkel tree changes? An arbitrary element. How can we update the proof for element A5? Let's do an example. Let's take A12, for example, where we just add delta to this element. We change it. Now, you can easily identify which elements of A5 proof are affected. And you can go ahead and recompute, in particular, this element here will be affected. You can go ahead and recompute the proof. In other words, a single membership proof can be updated in logarithmic time for Merkel trees whenever any element of the Merkel tree changes. Okay. So let's do something more complicated. Let's go do a range proof. So a range proof is a proof of a Merkel tree, in a Merkel tree, that proves that a specific range of elements belong to the range tree, to the Merkel tree. So let's take an example here. We want to prove that elements A3 and to A8, a specific set of set of elements belong to the tree. We want to prove that A3 through 8 belong to the Merkel tree. What we can do is we can provide a Merkel proof for A3, right? And we can provide a Merkel proof for A9. Okay, so a logarithmic size proof can be used to prove an arbitrary range of successive elements in the Merkel tree. Okay, this is a well-studied primitive, Merkel range proofs. Okay, now again, the focus of my talk is updates, so let's try to update this proof whenever an element changes. Let's pick element A12. If you try to update the range proof for elements A3 through A7, then what you're going to end up having is, again, a logarithmic time computation to update the range proof. Only a logarithmic number of nodes can be affected. Okay? So what I have done so far, I've told you about Merkel membership proofs, and I told you about Merkel range proofs, and I convinced you that both of these can be updated in logarithmic time when an arbitrary element of the tree changes. All right. Now, what we're building is what we call a batch proof. What's the difference of a batch proof with a range proof? A batch proof is a single proof of k arbitrary elements in the Merkel tree, not a successive set of elements, arbitrary. That's very important. And a batch proof should be smaller than k individual proofs. We don't want to give k individual proofs. It needs to be independent of the number of elements in the proof. And again, I'm going to talk about updates, right? So the ones that the batch proof we know so far are not updatable efficiently. In other words, for the batch proofs that we know so far, if you change an element in the Merkel tree, then you have to recompute the whole batch proof from scratch. And this is what we want to address today. So our contributions is we're gonna propose a new way to compute batch Merkel proofs using recursive snarks. The batch Merkel proofs will be updatable in logarithmic time whenever either an element of the batch changes or an element out of the batch changes, okay? We're going to present some application of this approach in verifying MapReduce style computations on dynamic data. So for example, I can provide a proof that proves to me the number of elements in the Merkel tree that is greater than 5, or it satisfies an arbitrary predicate. Okay? And of course, this proof is updatable. If an element goes above 5, say below 5, then the count changes, and you can recompute the proof without having to do everything from scratch. You can recompute this proof in logarithmic time. Okay, we're going to give two applications of our approach. One is on dynamic aggregate BLS key, and the other one is on dynamic digest translation. And I'm going to talk more about these applications now. All right, so how we compute a batch proof with our approach. To make things easier, I'm going to show you how to come up with an inefficient batch proof, right? A batch proof that is big, okay? So let's see, we want to compute a batch proof on an arbitrary set of elements, namely A2, A4, A5, A15. They're not successive, right? So what I'm going to do is I'm going to provide the individual Merkel proofs for every one of these elements. Again, this is not what we're going to do. I'm just making it easy for the presentation, right? So we provide the membership proof for A2, the membership proof for A4, the membership proof for A5, and the membership proof for A15. Okay, so you can figure out all these hashes correspond to the union of the membership proofs of the individual elements at the leaves. Right, so this is an inefficient batch proof. Now, how do we verify an inefficient batch proof? And in general, any batch proof, there's inputs and there's outputs, right? The inputs is the digest of the Merkel tree, a claimed subset of the Merkel leaves, S, the height of the Merkel tree, and some auxiliary witness width, okay? And the verification should output yes, if and only if S is indeed a subset of some Merkel tree of L levels whose digest is C, and no otherwise. All right? So I'm going to present to you two verification algorithms, one with a standard approach where the witness is just the Merkel membership proofs, and one with our approach where the witness is Merkel membership proofs plus some additional information that we call node subsets. Okay? So the standard approach, I'm sure you're all familiar with, this is the witness. These are all the individual Merkel proofs of the elements. So the way to do it is basically you start verifying every single membership proof one at a time, right? So for example, you verify the membership proof for A3, then you verify the membership, for A2, then the membership proof for A4 and A5, and then the membership proof for A15. If all these membership proofs verify, right, then you accept the batch proof, the inefficient batch proof, otherwise you say no. All right? Now, how do you turn this batch proof to an efficient batch proof? Well, you take all these proofs and you snark the verification algorithm. Basically, you snark every single Merkel membership proof, right? And then due to the snarks, say use, for example, growth 16, you end up with a small batch proof. But the disadvantage is that if you want to update this batch proof, because, for example, some element goes out of the batch, some element in the Merkel tree changes, then you need to recompute this batch proof from scratch. This is linear in the size of the batch. This is very inefficient. In particular, also, using a snark circuit assumes you have a static batch size, because if you change the batch size, you need to change the size of the circuit, because this is the number of Merkel membership proofs that you input to the circuit. So this might require, for example, if you use like a growth 16 snark, to run a new trusted setup from scratch. Okay? So again, the standard approach, efficient batch proof, has all these disadvantages that we're looking to address. So our approach, to talk about our approach, I need to define some things first. Okay, so say, for example, S is the set of elements in the batch. I'm going to define a node subset of a node V in the Merkel tree with respect to S. So now, every node in the Merkel tree will not have a hash. We'll also have a function, which we call node subset. It's a subset that is defined with respect to the claimed batch. Okay? The definition is extremely natural. So basically, the node subset of node V in the Merkel tree with respect to S is the subset of S in the subtree rooted at V. Okay? So the node subset of the root is S. The node subset of the left sibling is the subset of S that is rooted on the left sibling, and so on and so forth. Okay? Right. Okay, so now our inefficient batch proof now, the new inefficient batch proof, not only contains these membership proofs like we talked before, but also contains these node subsets. Okay? So the root here contains A2, A4, A5, A15. The CL here, A2, A4, A5, A15, right, and so on and so forth. So you can see basically that this invariant satisfied where every node has a node subset that is a subset of the initial claimed batch. Okay? So this is our new inefficient batch proof. So how do we verify it? Well, we start from the root. And first of all, what we're going to do is we're going to check that C is the hash of CL and CR. Okay? And then the next thing we do is we check to see whether the union of the node subset of the root is equal, the node subset of the root is equal to the union of the node subset of the children. We continue like this. We check whether the node subset of the left child is equal to the union of the node subset of the left child and the right child, and we continue this process, right? And eventually we reach at the leaves, where at the leaves, what we need to do is to check whether the node subset is equal to the element of the tree, right? This is for node subsets that are not empty, okay? So this is how our new verification works. Now, how do we turn this into an efficient batch proof? We're going to use the notion of a recursive snark. And I'm going to present to you the recursive circuit. Okay? So the public input of the circuit is, again, the digest of the Merkel tree, the subset S, which is the claimed batch, and the number of levels of the Merkel tree. The witness is the digest of the left node of the root, CL, the node subset SL, the level of the left node, and a proof PL, a snark proof PL, that proves that indeed SL is the node subset of a Merkel tree of LL levels whose digest is CL. Okay? And similarly for the right child. Okay? So the computation of the circuit goes as follows. It first checks that L equals LL plus 1 and L equals LR plus 1. Then it actually checks that the C is the hash of CL and CR. It checks the union. And then it says, look, if I have reached the leaf level, just check and make sure that the SL equals the actual data at the leaves. If not, just verify what I'm giving, right? So verify that indeed the witness is indeed a true statement for the left node and a true statement for the right node. So this is exactly the circuit that we're implementing. Now, why we want to see things this way? Okay? Because now we can build this batch-proof data structure. Okay? So say, for example, want to compute a batch proof for a tree, and the batch is exactly A2, A4, A5, and A15. Okay? The first thing that the prover needs to do is to compute the hashes and the node subsets. This is really trivial, right? I mean, you just compute the hashes, the individual hashes, and the node subset for every node. Okay? And then what the prover is going to do now is going to start computing these proofs for every node recursively, right? So every node is going to have this recursive proof computation that proves something about a statement of this node, right? So for example, the PLR proof proves that A4, A5 is some subset of the Merkel tree with digest CLR, okay? And so on and so forth until you end up with a final batch proof. And this is what our batch proof is. We define the batch proof as this P that it's the computation that we end up with the root. Okay, so that's our batch proof, is this red pie that is at the root. Now, this is the batch proof data structure, so how do we update this? So say, for example, we have an element, A5, that changes from A5 to A5 plus delta. What we need to do is we just go and update all the recursive proofs along the path. Okay? And this takes logarithmic time. So we can update this batch proof in logarithmic time. So this is basically the main insight. All right, so we have a bunch of optimizations. For example, we use, because we have to deal with circuits, we don't use actual sets, but we use accumulations. We can use accumulators for every node. We didn't use like a number theoretic accumulator. We just use hashing because this is what circuits can do faster. And well, actually, instead of having a single circuit, because the computation of the leaves is much smaller, so we have two different circuits, and we pass a different verification key depending on the level we are. So these are some optimizations that we implemented. And now, applications of this. So the batch proof computation can be seen as a special case of a more general map-reduced computation, where the map computation at the leaf level takes as input the claimed batch and decides whether the leaf belongs in the batch or not, outputting the set, the leaf itself if yes, and nothing if not. And the reduced computation just computes the union of whatever you get from below, right? So we can, with this observation, we can generalize our framework for any arbitrary map-reduced computation on any subset of data elements of a Merkel tree, okay? So we basically have a map computation of the leaf, and we have a reduced computation, and we can attach proofs for every node, internal node in the tree. And eventually, we get a proof that the output of a map-reduced computation on a specific subset of a Merkel tree whose digest is a specific value is this. Now, of course, you can get this proof with other things as well, but the good thing here is, again, if you change an element, A6, you can update this proof for any arbitrary computation. You don't have to recompute it from scratch, okay? First application is we apply this MapReduce on an aggregated BLS public key. So here is exactly what we want to solve. So say the BLS public keys of n validators are stored in the memory of a smart contract, okay? And someone comes up with an aggregate public key and makes a claim. The claim is this aggregate public key is an aggregation of a T-size set of some subset of the Merkel tree, right? So subset S can change across blocks, and the way to do it, so actually this is exactly the statement we're proving, that APK is the aggregated BLS public key of T public keys that belong to some Merkel tree of n public keys whose root Merkel digest is C. So we just care about the number, okay? So the way to do it now is, again, we're going to run this map-reduced computation where the map at the leaf level basically outputs 1 if the specific key participated in the specific aggregation of public key, and then output 0 otherwise, and then you go up and you just add the counters, right? Add the counters, and then you can prove that you have an aggregate public key that is an aggregation of some set of 3 public keys that are stored in the Merkel tree of this specific digest. Again, computable with other approaches, but what we can do here is we can update this proof as signers come in and out. So someone can for the next block, someone can decide not to sign, right? And someone can decide to sign, right? So you can have the set increasing or decreasing, and what you can do is you can update this proof in logarithmic time, okay? Another application is this notion of digest translation, where we basically have n values in the Merkel tree, and we have a Merkel digest computing with SAT56, which is an expensive hash function. We have another digest that is computed with Poseidon. And we want to produce a proof that these two digests are consistent. In other words, they represent the same elements at the leaves. Again, you can compute this proof, but what we're doing here is as the blocks come in and these values change, we can update these proofs in logarithmic time without having to recompute this from scratch. Okay. Right, so here it's the same pictorial representation. Right, so we have some preliminary evaluation. We implemented this recursive snark proof with Plonky 2. We also, this computation aggregation is embarrassingly parallel, so we did a distributed implementation of our protocol. So the distributed implementation, we're able to achieve a speed up of 10x. I'm confident we can go above that. I mean, that is a very preliminary implementation. The batch proof size is 45 kilobytes with Plonky 2. And right, so here are some numbers. So the aggregation itself, computing the batch proof, is 3 times slower than the Merkel snark proof. This is the price you have to pay for the updatability. Okay, this is something to be expected. The verification is 40 times faster than the Merkel snark approach. This has to do with the fact that the verify algorithm doesn't have to do any group operations. It just computes like this hash accumulator outside of the snark. And the update of a single proof is 35 seconds, 53 times faster than Merkel snarks, and 135 faster than Merkel snarks whenever the batch size changes, because then you have to run like a new trusted setup. Okay. And these plots are for n, the number of leaves in the Merkel tree is 2 to the 29, and the batch is 2 to the 14, randomly generated leaves. Right, so this is what we compute here. All right, and with this, I'd like to finish. You can find the paper in this website, and be happy to take any questions.
Any? Yeah.
Hey, Bobbies. So for the Merkel snark construction in your experiments, what is Merkel snark? What hash function? What proof system?
The hash function is Poseidon.
Poseidon.
Yes, and the proof system is Gro16.
Gro16. Okay.
Right.
Thanks.
So this idea seems to be generalizable to a tree-based vector commitments, right? So have you thought about
where?
To generalizable to tree-based vector commitments? Have you thought about implementing it for Merkel trees? Like for that will be used in Ethereum?
So actually, the underlying vector commitment we're using in this construction is actually a Merkel tree. We use a Merkel tree as an underlying vector commitment. So it is, right, so it is actually meant for tree-based vector commitment.
Yeah, so the question was on Merkel trees.
On Merkel trees, yes.
Yeah,
Merkel trees, I'm sorry.
Yeah.
Yes, yes. This is actually something that we're looking into. Yeah.
What is typically the number of elements in that tree that we are looking at?
The number of leaves, or the number of leaves, we run some experiment for n 2 to the 30.
Okay.
Right.
Thank you.
I think you said the time for, over here. The time for updating the proofs was 30 seconds or
Right,
so?
right.
Are you having to like construct the whole tree before?
No.
Okay.
This has to do with the cost of the recursive call.
Sorry, what?
Right, so you only do computation along the path. Right. So
Gotcha.
you don't have to reconstruct the...
So there's, when you add this like node set construction to the tree, that, do you have to you don't have to Merkelize that. That's just a attachment to the Merkel tree.
Yes,
Okay,
yes, that's
gotcha.
right. Yes, yes, yes.
Let me ask a question then. So BLS key aggregation seems like a powerful primitive. What are your thoughts about actually deploying it?
Right, right. So basically, there are some consensus protocols where the validity of the next block depends on the number of signatures of a specific set of validators, right? And potentially in a cross-chain application, when you want to prove the state of a different blockchain, as the blocks keep coming in, potentially this could be an application, and this is something that we're looking to deploy.
Okay, let's thank Babis. Okay, our next talk is entitled Threshold Signatures from Inner Product Arguments, Succinct, Weighted, and Multi-Threshold. The talk will be given by Ling Ren from University of Illinois, Urbana-Champaign.
Thanks for the introduction, Ari. It's a pleasure to be here to tell you about our recent work on threshold signatures from inner product arguments. Okay, so let me start with threshold signatures. So this is a cryptographic primitive introduced first in the 80s and 90s. By now, it's fairly standard. The idea here is that we have a group of signers, let's say n signers. They want to sign the same message. Of course, we can have each of them sign and put all of their signatures in a list, and that would be a naive threshold signature, but we can do much better. So there are schemes that allows these signers to each send what we call a partial signature to an untrusted aggregator, and the aggregator can combine these partial signatures together and produce one final signature that we call sigma here. And a valid threshold signature sigma, this has a constant size, it basically vouches that indeed many of the individual signers have signed. And we call it a NT threshold signature if the signature proves that T out of the N signers have signed the message. Okay. So threshold signature has many applications. The most relevant ones to blockchain and to SBC are the following. So first, we can do a jointly held wallets. Think of a Bitcoin wallet or Ethereum wallet, where you may want multiple people to control this wallet, and multiple of them need to give their approval before you can transfer funds out of the wallet. So the other major application of threshold signature is Byzantine fault-tolerant consensus protocols. So you're probably familiar with the longest chain style of consensus protocols. The other major category is the classic BFT, where we routinely have steps where we want multiple people, half of the nodes to sign the same message, or 2/3 of the nodes to sign the same message. And that is exactly what the threshold signature can give us. Okay. And we also have pretty efficient threshold signature constructions. Most of the existing ones rely on Shamir secret sharing. The idea here is that we start with the single signing key, and then we'll use secret sharing to divide it into n shares, and then we give one share to each signer. And the promise of secret sharing is that T of these signers can come together and use the secret key to produce a signature, but T minus one of them cannot learn anything, cannot do anything with the secret key. Okay? And the Shamir secret sharing based threshold signatures give us a very efficient threshold signature scheme. The signing time for each signer is a constant, and the aggregation time is quasi-linear, usually n log n, and the signature size is also constant, and the verifier does very little work to verify the signature. Okay? So everything is great. But in this talk, in this work, we would like to have threshold signatures with a few extra properties. The most important one for us is weighted signing. Right? By that I mean we will have the same setting, pretty much the same setup as threshold signatures, but now we no longer treat each signer equally. Right? We'll assign a weight for each signer. And again, they will send their partial signatures to aggregator and produce a final signature, weighted threshold signature. This time, a valid signature vouches that signers with a combined weight at least t have signed the message. And this can extend applications of threshold signatures from the classic BFT protocols to a proof-of-stake BFT protocol. Right? In BFT proof-of-stake protocols, we want the signing power to be proportional to the stake that each signer has, each validator has. Right? So that's the application for weighted threshold signature, right? Where you can think of the weights as the stake. Okay, so now, but for weighted threshold signature, right, suddenly we don't have a good construction anymore. And it's also a bit unclear how we're going to go about solving it. But let me first give you a few naive constructions. Right. So the one natural idea to construct a weighted threshold signature is to rely on this notion called virtualization. Right. The idea here is simple. If somebody has a weight of 3, we will just ask that person to pretend to be 3 people. Right? If you have a weight of 50, then you play the roles of 50 different virtual signers. Right? This is why it's called virtualization. Now, if you do this, now we're back to the unweighted setting of threshold signature, and we can use any unweighted threshold signature out of a black box, right? And the rest is same as before. Right. But this construction has a few major problems. Right. The first one, mostly efficiency. The first one is that the signing time is now proportional to the weight of each individual signer. It's no longer a constant. The aggregation time is proportional to the total weight in the system. And last one, there's actually a step called distributed key generation that you can think of it as an initialization or setup stage if we want to use Shamir secret sharing-based threshold signature. I didn't mention, but these individual signing keys, they are not independent. They have to live on a low-degree polynomial. Right? So the signers actually have to run the interactive protocol to make sure that their signing keys are correlated in the right way. Right, so this is usually, it's actually already a non-trivial step even in unweighted threshold signature, but now we suddenly blow up the number of virtual signers by quite a large factor, and then this DKG, distributed key generation step, will by far be the biggest bottleneck. Okay, so to put these efficiency problems into perspective, so here I'm showing a few examples. Proof-of-stake and proof-of-space blockchains that would have benefited from weighted threshold signature. Right. What you can observe here is that the number of parties in these systems are usually on the order of hundreds and thousands, right? But the total weight of the system is several orders of magnitude larger, right? Often in the billions. Right. So if you use this virtualization technique, then the per signing cost could be up to 1 minute. Right? Some signers may have to play the roles of 1 million virtual signers. And the aggregation cost now is also proportional to this on a range of billion. That would be at least 10 minutes. And the DKG is even worse because this is a procedure that's cubic in complexity, and that's going to take hundreds of years. So this wouldn't work. But let me also mention that there is another limitation we hope to address or fix in traditional threshold signature. That is, it can only do a single threshold. Right? Because we need to set up their secret keys. If your secret keys, signing keys, are set up to produce threshold T signature, that's the only threshold you can produce. Right? Whereas we have some new applications that call for multiple dynamic thresholds. Right? So in these applications, sometimes we want half of the people to sign, sometimes we want 2/3 to sign, or sometimes 3/4, actually anywhere in between. Right? So a traditional threshold signature wouldn't support such a use case of multiple dynamic thresholds. Okay, so the virtualization approach doesn't quite work well. Right? So let's try something else. Right? So there is an alternative approach that's fairly similar to threshold signature called multi-signatures. Okay? And so first, it immediately offers advantage. We no longer need DKG or correlated keys. In multi-signatures, these signing keys for different parties are independently generated. Okay, and next, they each produce a partial signature. This is very similar to what we have seen before, and the aggregator aggregates these and send to the verifier, right? But not only the signature, but also a bit vector, right? Indicating who signed and who didn't. Right? In this example, party 1 and 2 signed, party 3 didn't sign, right? So that we have a bit vector 1, 1, 0, etc. Okay. But in multi-signature, the verifier needs to do more work. So first, it needs to keep track of this list of signers and their public keys. Right? And the verifier needs to do an aggregation of the public keys. This is actually something the previous talk just covered. Right? The aggregator needs to multiply these public keys together. And once she does that, the verification of the signature is fairly simple. It's 2 pairing operations. And this approach of multi-signatures offers several advantages. Importantly, it supports weighted signing and dynamic thresholds very easily. Right? So if you want to add weight to this system, we just assign weights, and we have another weight vector also at the verifier. And the verifier additionally needs to sum up these weights based on the bit vector, who signed, who didn't, and we can easily check if the combined weight reaches the required threshold. Okay. Now, what's the problem here? Right? Once again, it's efficiency. Right? Signing time, aggregation time are pretty good, but verification is now problematic. Right? So there are two parts of that. The verifier needs to dedicate a lot of storage to keep this vector of public keys and weights. It also needs to do linear computation. Right? And in many cases of blockchain applications, we want the verifier to be lightweight. Okay, so the multi-signature scheme also doesn't quite give us what we wanted, but it will be the starting point of our approach. Okay? And we will bring inner product arguments into the construction of multi-signature to get an efficient weighted threshold signature. Okay? And so here it is again. This is the multi-signature scheme from the last slide. Right? The basic idea is actually very simple. Right? We'll take this linear computation step, that's our bottleneck. Right? We want to lift this responsibility from the verifier and give this task to the aggregator. So the aggregator is already doing linear work, so it's not a big deal to add more linear work to the aggregator. Okay? But now the aggregator is responsible for computing the aggregated public keys and the weight, combined weight. So it's going to send to the verifier the signature, this aggregated public key, APK, and the weight T, along with a proof, pi. Right? That basically proves to the verifier that the aggregator computed these two things correctly. Okay. Now, in order to verify this proof, the verifier also no longer has to keep these two long vectors. It just needs two succinct representations, right, what we call commitments, to these two vectors. Right, and it can verify this proof efficiently. Okay, so this is our basic idea. Okay, I said inner product arguments quite a few times. What do I mean by that? Notice that on the right-hand side, we have this combined weight T that's a summation of individual weight. Right? That can be written as a summation of Bi, Wi. Right? So that is the inner product between two vectors, right? Between the bit vector indicating who signed and the weight vector. And on the left here, this aggregated public key that doesn't quite look like inner product yet, but notice that each public key, G to the Si, that's a group element, right? So this product of G to the Si, that's actually how inner product should be defined between a vector of group elements and a vector of field elements, or integers. Right. So both of these statements that the aggregator wants to prove are actually inner product statements. And there's something that could be easily missed, that the proof actually has to contain a third component, that is this bit vector B is actually a binary vector. Right. Every element in the vector is either 0 or 1. Okay, so now we successfully reduced the problem of multi-signatures to inner product arguments. Right? And this is the interface of inner product arguments. There's a prover who has two vectors, A and B, and the verifier has two commitments, CA and CB. And the prover computes the inner product, sends the inner product together with the proof to the verifier, and the verifier checks the proof and be convinced that the inner product is correctly computed. Right? And there are many inner product argument constructions out there. So it's a natural idea. Right? We can just use one of these or two of these inner product arguments, and then we'll be good to go. But unfortunately, that's not the end of the story, because the inner product arguments for field elements or for integers are fairly efficient, but the IPA for vectors of group elements and field elements turns out to be fairly expensive. Right? And I'll come back to this and show you how much of a bottleneck that is. Right? But this is, would be the next problem we want to address. Okay, so let's take another look at our bottleneck here. We have an inner product between a vector of group elements and the vector of integers. Right? So right now, we have been writing it as this group and field inner product. But notice that our group elements are actually not generic group elements. They have a very special form. Right? So there is another way to write these things. That is, we can write it as a G raised to that summation of BI-SI. Right? So now it becomes an inner product between two integer vectors, right? Two field element vectors. But it's on the exponent. Right? So it turns out it's not too hard to deal with something on the exponent. The real challenge here is that the verifier, or the prover, the aggregator, does not know one of these vectors. Right? This vector S, that's the vector of individual signing keys, and that must be kept secret. Okay? Now, luckily, we do have some players in the system who do know those signing keys. Right? So the individual signers collectively know this secret key vector S. Right? So they can help the aggregator compute the proof. Due to time constraints, I wouldn't be able to tell you the entire construction and the math behind it. Right? But here's just one sample step. Somewhere in this proof generation step, we need to compute something like that. Right? What I want to draw your attention to is that there is a component there that's something raised to Si. Right? That is a value that the aggregator cannot compute because it doesn't know this Si value. Right? But signer I knows that value. Right? So signer I can compute this G to the L to the Si value and send it to the aggregator to help the aggregator. Now, every signers help the aggregator, and aggregator will be able to compute this proof this way. I think one remaining problem is that we have linear such steps, and each one require linear computation, so that would have been a quadratic total cost. But it turns out we can find a way to make most of these quadratic costs a one-time pre-processing, right, and have the online aggregation cost to be quasi-linear, again, n log n. All right, so that would be our final scheme. Right, so on the left, we have the aggregator who have these three vectors, a vector of public keys, a vector of weights, a vector of bit vector who signed, indicating who signed. On the right, the verifier has the commitments of those two vectors. And here is the final signature. Right, so there's a threshold combined signature. Right, there's a proof that the B vector is binary, a proof that the threshold T is computed correctly, and a proof that the aggregated public key is computed correctly. Right. Right. So this goes back to these three things we want the aggregator to do and to prove that it did so correctly. Okay, right, so we can do a quick count. We have 9 things over there. 8 of them are group elements, and 1 of them is an integer. Right, so that is the final efficiency of our scheme. Right, our signature size is 8 group elements plus 1 integer. Verification key size is 7 group elements. Verifier time is 8 group elements plus 8 pairing operations. Signing cost is constant. Aggregation cost is n log n. Now, to put that cost into perspective, I'd like to compare with 2 things. Right, so the second row is what the cost would have been had we used a black box group and element and field element IPA. Right, so this is the expensive IPA I was referring to. Had we done that, our signature size and verifier time would become logarithmic. Right, and what's worse is that they will involve operations in the target group. Right, and this would be at least 2 orders of magnitude worse than what we got. Right? 1 order from the log n, 1 order from the group element. Right, and on the last row, I also like to compare with the unweighted BLS threshold signature. Right? As you can see here, our signing time and aggregation time are pretty much identical. Right? Our signature size, verification key size, and verifier time are slightly worse. Right? Worse by a reasonable constant factor. Now, if we compare with existing previous weighted threshold signature schemes, you will see the huge advantage we get. If we use virtualization, then aggregation and signing would be prohibitive. And if we use multi-signature, then the verification key and verifier time would be very costly. Right. And so here's experimental evaluation. We tried this for 4,096 signers. Right. As you can see here, our efficiency is fairly similar to BLS. Well, aggregation time is fairly similar, and everything else is small constant factor worse, as expected. Right? Whereas all the other schemes, right, multi-signature is very bad in terms of verification key size. And growth 16, this is a generic SNAR construction. The aggregation time, the prover time, will be prohibitive. And there is another prior work called compact certificate that has a very large signature size. And these savings will translate to gas savings if we deploy this on a smart contract, right? And we tried that. And signature verification using our construction would cost something like 800K gas, right? But if we use a multi-signature, the cost would have been several orders of magnitude higher. All right, that's all I want to tell you about our threshold signature scheme from inner product arguments. It is a new paradigm to build threshold signature. It has a few advantages: no DKG, arbitrary weights, and support dynamic thresholds. It does still have a few limitations, so these are good open problems. Right? One of them is the preprocessing. Right? We need a one-time quadratic preprocessing. Sometimes it's okay, but if we want to frequently change the set of signers, then this would be a bottleneck. Okay? And the other one is that we don't have security in the standard model yet. We have to make some relatively strong assumptions called algebraic group model. Right. So yeah, if you are interested in more details about our construction, I encourage you to check out our code and paper. And I also want to give a shout out to a concurrent work by Sanjay Garg, Abhishek Jain, and others who pretty much proposed the exact same construction just a few days apart from our work. Okay. And yeah, and that will conclude my talk. Happy to take questions.
Seeing that you left out all the tasty bits on exactly how the setup goes and everything like that, and I took the liberty of reading the paper beforehand, the setup involves initializing some Lagrange polynomials that have knowledge of the entire signing set, correct?
Yes, the preprocessing step is, yeah, we need to compute a bunch of values and usually using Lagrange interpolation. And yeah, we routinely raise the Lagrange polynomials to individual signing keys. So these need to be contributed from the individual signers, and the aggregator will combine them into.
Okay, so is that process interactive?
It doesn't have to be. It's 2 rounds. Every signer posts the helper data, and the aggregator take all the helper data and produce the final values. Right? In fact, in this concurrent work, that they believe that's the primary advantage of this construction over existing DKG-based ones. They call it the silent or one-round setup.
So understanding that, then, if you have new, in an application sense, new validators entering into the set, do you have to run through a new setup procedure, or is it updatable?
Right now, it's we have to redo the setup. We don't know how to do it, make it incremental.
Okay, thank you.
Thanks for the great talk. I was curious if in some settings it makes sense for the aggregator to not be aware of the weights of the party. So you have the weights, but the weights are private. Do you think that's important, and could your scheme be extended perhaps to include that?
Yeah, I think in principle it's possible because the aggregator produced the proof regarding the secret keys without knowing the secret keys, right? So then if the aggregator doesn't know the weights, somebody has to know, right? Somebody has to, again, do this help thing, help the aggregator generate the proofs regarding the weights.
So could that not come from the individual signing key holders themselves to have perhaps the weight be inherent in the key itself?
It will have to come from whoever that does know the weights.
Yeah, thanks.
Hey, Ling, really, really cool work. I have 2 questions. So you mentioned how the signers help the aggregator by sending some auxiliary information over. So this is just part of their signature share, right? It does not require any back and forth interaction between the aggregator and the
Right, it's a
signers.
one-round interaction. It's the signers post the helper data, and the aggregator take them and do the preprocessing.
I see. So it doesn't add more interaction.
It doesn't have more interaction. Yeah.
And for your slide 20, where you have your performance numbers, I guess it's not on the screen anymore. You have a BLS threshold aggregation time. What aggregation algorithm are you using? Are you using the t-squared algorithm or the t-log squared t algorithm?
The n log n Lagrange interpolation.
Lagrange interpolation is not n log n as far as I know, but I'd be curious to see which n
Yeah, I
log n.
believe that we use the what do they call it? Roots of unity.
Sorry?
Roots of unity and FFT.
Yeah, but there's a t-log squared t step that arises at some point in that algorithm.
Yeah, that's what I meant. The t log t.
Okay.
Yeah.
Okay, cool. So that's the one you're using?
Yes.
Okay, cool.
Okay, let's thank our speaker. Okay, our final talk of the session is entitled Security Analysis of Filecoin's Expected Consensus in the Byzantine versus Honest Model. And the speaker is Shuchao Wang. Affiliation is Hong Kong University, is that correct? Okay.
Okay, good afternoon, everyone. My name is Shuchao Wang. I'm a faculty member at Hong Kong University of Science and Technology. So today, the title of my presentation is Security Analysis of Filecoin's Expected Consensus in the Byzantine versus Honest Model. So this is a joint work with Sarah and Merkel from Protocol Labs. And this work was also done when I interned there last summer. So this work will be forthcoming in Advances in Financial Technology, or AFT 2023. Okay, let's get started. So Filecoin is currently the largest storage-based blockchain in terms of both the storage capacity and the market cap. And in Filecoin, the storage miner gained the right to propose a block or participate in a consensus protocol and propose a block by pledging the storage capacity to the Filecoin blockchain. So, and whenever their block is proposed and enter the Filecoin blockchain, then the Filecoin miners will be compensated with the underlying cryptocurrency of Filecoin. And Filecoin uses this so-called storage power consensus, which mainly consists of two components. So the first one is a stable resistance mechanism called proof of storage. And this mechanism keeps an accurate table of the storage power or storage capacity pledged by each participant, called storage miners in Filecoin. And the second component is a consensus protocol called expected consensus, or EC. So EC can be run by any set of weighted participants. And the consensus will output a list, order list of transactions or a total ordered ledger. So the focus of this talk is to attack and analyze this consensus protocol expected consensus. So as I said, that EC can be run by like any set or list of participants weighted by their storage power. So here, relying on the proof of storage mechanism in Filecoin, so we can actually construct this power table. Like this is a screenshot from the Filecoin website. And so with this power table, actually, we can just treat the expected consensus as a proof of stake consensus. And for simplicity, in this work, we will assume a static power table in this work. And every consensus protocol needs a leader election mechanism. So in Filecoin, they use a DRAND protocol called decentralized random beacon. So it's a public random beacon. It generates a random value every 30 seconds. And then Filecoin uses the VRF function to do the leader election. So whenever the output of this VRF is less than a certain target, then the storage miner will be elected as a leader and will be able to propose a block. So if you are not familiar with VRF, then you can just think this leader election as a public lottery. So this lottery will use a public random value derived or obtained from this random beacon, and the leader elected from this random beacon will be just like the winner of this lottery. And the target in this lottery is set to such that on average, on expectation, there are 5 leaders per epoch. And since now we have multiple leaders in one epoch, so now we actually allow multiple blocks on the same height or on the same height of the blockchain. So now the blockchain in Filecoin is actually a DAG, directed acyclic graph, instead of a single blockchain. So now Filecoin introduced the notion of the tip sets. So basically, a set of blocks will form a tip set if they appear on the same height or they are mined in the same epoch, and at the same time, if this set of blocks they have the same parent tip set. Like for example, on this simple DAG on these slides, we have multiple tip sets, like the block A, block B, and block C will form a tip set in the first epoch because they all have the genesis block as the parent. And then block D and block E will also form a tip set because they have a common parent tip set, that is block A, B, and C. And then for the same reason, like block F, G, H will also form a tip set. So now the blockchain in expected consensus or in Filecoin is actually a chain of tip sets instead of a chain of blocks. So and for the fork choice rule, so Filecoin uses the heaviest chain rule instead of the longest chain rule like in Nakamoto consensus. So here we simply counting the number of blocks in the blockchain. And here let's take a look at this a little bit more complicated DAG. So in this DAG we have a lot of tip sets. For example, the block ABC, and actually all its subsets will form a tip set. And block D and block E will also form a tip set because they both have block A and block B as the parent blocks. And at the same time, block F itself will be a tip set because the parent of block F is actually the tip set ABC. So you can actually find like two chains of tip sets in this DAG. So the first one starts with the genesis block, and then in the first epoch we have block A and block B, and then in the second epoch we have block D and block E. And we can actually have another chain of tip set. So start from the genesis block, and we can use block ABC as the first tip set in the first epoch, and then in the second epoch the block F will be the tip set. And if you count the weight of these two blockchains, then both of them actually have like 5 blocks, so they have equal weight. So we need a tie-breaking rule. So we made a standard assumption in our work that the tie-breaking rule will always favor the adversary. Not that this is a standard assumption in many other like long decision style protocols, and this assumption only makes the adversary stronger. Okay, now you may ask like why EC, like what is the logic behind like having the notion of tip set? Why not just using the long decision protocol like in Nakamoto consensus? So perhaps the first advantage of having tip set is that in Filecoin, the miners will be elected more often. Like right now, we have like 5 leaders elected for every 30 seconds. So, and we know that in Bitcoin, like the Bitcoin miners will join the mining pool to fight with the mining variance. And in Filecoin, the mining variance is much lower because the leaders are elected much more frequent. And maybe the second benefit of having tip set is that in this way, like the private attack will be harder. So by private attack, I mean in the attack, the attacker will try to mine a blockchain in private and only release this private chain when its weight is larger than the public chain. So basically, this is the same intuition as Ghost. So Ghost for the famous greedy, heaviest observable subtree. So Ghost was proposed like to be secure against the private attack as long as we have an honest majority assumption, and no matter like how large is the block rate. And we can expect the same result that the EC, the expected consensus, is always secure against the 50% adversary if the attacker is doing the private attack, because like the weight of the public chain will always grow faster than the weight of the private chain. But from the lesson of Ghost, we also learned that like having a DAG or having a complex blockchain structure also may enable a larger attack space. So we may have to worry about the same issue with EC, like just like in Ghost. So indeed, I will show you a couple of examples, a couple of attacks on EC. So the first one is called the private attack with a head start. So let's look at this tag on these slides. So here the red blocks are adversarial blocks, and the green blocks are honest blocks. And we can see that in this tag, we have two chains of tip set. The first one ends at block H. So it starts with the tip set block A, B, C, D in the first epoch. And then in the second epoch, we have block E. And then in the last epoch, we have block H. And the other chain of tip set ends at block I. It consists of all the honest blocks, block C, D, F, G, and block I. And you can see that here, although the block C and the block D are mined by the honest miners, they are actually shared by both chains of tip sets. So, and if you count the number of blocks mined by the honest node and the attacker in this graph, you can see that the attacker actually only mines 4 blocks, and the honest node mines like 5 blocks. But still, the weight of this attacker chain ends at block H is larger than the public honest chain. So in this attack, the attacker will succeed even if the attacker mines less block than the honest node. So this is because the adversary can kind of leverage like some honest blocks mined in the first epoch as a head start. So this gives an unfair advantage to the attacker. And another example of attack on EC is the balance attack. So essentially, like EC is a proof of stake protocol because assuming we have a power table. So the attacker in EC can actually equivocate. They can propose like multiple blocks with the same block header or the same block winning ticket from the rotary, but these blocks will have different block content. Like here in this example, block B1, B2, B3, they all proposed with the same winning ticket, but they are equivocating blocks. So in this way, the attacker can kind of split the power of the honest node to make sure that the honest nodes are working on different block chains, and so now we have multiple block chains with equal weight, and assuming that the attacker can further like breaks the tie to whatever like extent it wants. So the blockchain may never converge, and none of these blockchains will be stabilized. So this is called the balance attack. So therefore, after seeing these two attacks, we know that analyzing EC is kind of tricky because of the large attack space, and we cannot naively claim that EC is secure against a 50% adversary by only analyzing the private attack. So we need a formal security analysis on EC. So let's do some math or do some analysis. So first, we need a model. So here, in this work, we assume a lockstep synchronous network model. So this is works that in EC, we use the DRAND, which is a synchronized random beacon. Here, the DRAND has a fixed size epoch that is 30 seconds. So it's reasonable to assume a lockstep synchronous model. And here, let beta be the adversarial storage fraction. So again, here we assume a static adversary for simplicity. And again, another parameter in expected consensus is M, which is the expected number of blocks in each epoch. And currently, M is set to be 5 in Filecoin. So, and in Filecoin in EC, the actual number of blocks mined in each epoch actually follows a Poisson distribution. So here, beta and M, these two parameters are all we need to do this analysis. And the main result of this work is that we prove that the EC is secure if and only if this inequality is true. So this means that we have a tight security analysis, and the security threshold for the protocol, we have a tight security threshold for EC. Okay, we obtained this result by extending the proof technique developed in one of my previous papers. So it's called Everything is a Race and Nakamoto Always Wins. So this paper was accepted in CCS 2020. And the first and very important step of this proof technique is called block tree partitioning. So let's first use the longest chain as an example. So here we can a general block tree is represented as multiple adversarial trees rooted at each of the honest block. So here on this figure, the honest blocks are marked with H0, H1, H2, and H3. And the adversarial blocks are those colored blocks. So in this way, like all possible attacks or all possible like block trees can be reduced to races between fictitious honest chain and multiple adversarial block trees rooted at each of these honest block. And here in the long chain protocol, we created the notion of Nakamoto block. So an honest block is called a Nakamoto block when all the adversarial block trees never catch up with this fictitious honest chain. And for example, like if from the birth of this block H7, like all the previous 4 adversarial block trees, T1, T0, T1, T3, and T5, they never catch up with the fictitious honest chain that contains block H7, then this honest block will be called a Nakamoto block. So here we have reduced like all possible attacks into like multiple races between the honest chain and the adversarial block tree. So here we have a race, so then we care about like the speed of each player in this race. So let me introduce some notation, like now let the HG be the growth rate of this fictitious honest chain, and the number AG be the growth rate of each of the adversarial block tree. So what we proved in this previous paper is that as long as number HG is larger than number AG, means that the fictitious honest chain grows faster than any of these adversarial block tree. Then we can show that Nakamoto block will occur infinitely often. So this means that the blockchain will converge and stabilize every now and then. And these Nakamoto blocks will stay in the long chain forever. And every time you can just treat a Nakamoto block as a new genesis block. And so in this way, we can conclude that the consensus protocol, the long chain protocol, is secure against all possible attacks. Okay, this is the proof technique we have from the previous work. And in this work, we extend the notion of Nakamoto block into something called Nakamoto epochs. And actually, the key step of this this extension is to identify a deterministic sufficient assumption condition for an epoch to be a Nakamoto epoch. And after that, we can follow exactly the same proof argument that if the fictitious honest chain grows faster than any of those adversarial block trees, then we can conclude that Nakamoto epochs will occur infinitely often, and the expected consensus will be secure against all possible attacks. So now the problem is reduced to derive like the speed of the growth rate of the fictitious honest chain and the adversarial block tree. So here for the honest chain growth, we use the worst case honest chain growth. That is, we may, like in the worst case, we may at most have 1 block in each epoch. So if you are familiar with the PDF or of the Poisson distribution, then you can see that here the worst case chain growth I showed here is the probability that the Poisson random variable is non-zero. And here and on the other side for the adversarial chain growth, it's not hard to see that the growth rate will simply be the power of the adversary, that is beta times m. So on expectation, there will be beta times m blocks per epoch mined by the adversary. So combined with the proof technique from the Everything is a Race paper, we can conclude that EC is actually secure as long as E minus e to the power of minus 1 minus beta m is larger than beta m. And actually, we found that this security threshold is actually also tight. So because we can find an attack that can achieve this threshold. So let's take a look at this so-called, we call it unsplit attack. So this basically is an extension of the balance attack on EC. So in this attack, the attacker will try to split the honest participants as much as possible. So perhaps it will split the honest chain into n blockchains, where n can be the number of honest miners. And in this way, the attacker will make sure that at most one honest block is mined in each epoch, because like every honest node is working on different chains. And we can see that in this way, the chain growth of this public blockchain is indeed the worst case chain growth. That is at most one honest block per epoch. And simultaneously, since the adversary can equivocate, so the attacker can actually grow and separate blockchain that contains all the adversarial blocks in its private chain. And this private chain will contain all the adversarial block, so the growth rate of this adversarial chain is indeed beta times m. So we can see that this attack will succeed as long as this inequality holds. So basically, this is the same condition as the security of EC we showed on the last slides. So okay, you may ask like this split attack looks like artificial, because it's actually detectable, because like the attacker needs to equivocate, and it will leave some cryptographic evidence, and everyone will know that the attacker is double signing. And just like many other consensus protocols, EC also has this slashing condition that will slash the equivocating attacker, but will this slashing really help? But unfortunately, the answer is no, because for two reasons. The first reason is that the attacker can try to create as many symbols as possible. Just make sure that every symbol only contains like the minimal storage that is required to participate in the protocol. And so in this way, during this attack, during the unsplit attack, only a very tiny fraction of storage power will be slashed by the slashing condition. And more importantly, actually this attack is not slashable at all, because this attack will also destroy the lifeless of the blockchain. So the fraud proof will not be able to submit it to the blockchain, and we are not able to slash the attacker. So okay, so now combining these two results, the possible result and the attack, we have found actually the necessary and sufficient condition for EC security, and basically they're the same. So we have a tight security threshold, and currently the parameter m in EC equal to 5. So this gives us a security threshold of about 0.196. So it's not ideal, but better than nothing. And if we set the parameter equals to 1, then EC almost becomes the long-chain protocol. Then the security threshold will also be boosted to about 0.433. And approximately, when m is large, the security threshold of this consensus of EC is about 1 over m. And we also propose a couple of mitigations to this split attack. The first one is simply just replace EC with the longer chain protocol, but still this requires a hard fork to the Filecoin client. And the second one is simply add a consistent or reliable broadcast to prevent the equivocation by the attacker. And this only requires a soft fork, so this mitigation is currently adopted by the Filecoin team. And the high-level idea of this mitigation is that the unsplit attack will not be possible if we prevent the adversary from equivocating. And here is the original implementation of a Filecoin client. So during, in the middle of this epoch, we have a cutoff time, and so the Filecoin node will only accept blocks before this cutoff time, and the blocks will be rejected after this cutoff time. And in our improvement proposal, we add a consistent broadcast mechanism protocol into one epoch. Basically, we add another cutoff time, that is this cutoff time 2. So the equivocating blocks will be discarded at this cutoff time. In this way, then we can guarantee that like 2 honest nodes will not accept like 2 equivocating blocks. So this improvement proposal has been recently merged into the Filecoin Lotus client. And however, currently we don't have a formal security analysis for EC with this consistent broadcast yet. So this still remains an open problem. So as a summary, in this work, we proved a tight security analysis for expected consensus. And currently with current parameter, so EC has about like 20% security. And there also remains some future work. Like the first one is that the security analysis of EC with the consistent broadcast. And the second one is that, in this work, we only consider the classic model of Byzantine versus honest nodes. And we did not address the incentive issue in EC. So to prove the incentive compatibility or incentive incompatibility of EC is another important aspect of understanding EC security. And the third future work is to relax some simplifying assumptions, like the lockstep synchronized model, or consider a more realistic tie-breaking rule, and maybe also consider adaptive adversary. Okay, so I would like to end here, and you can find my contact here, and feel free to drop me an email, and you can also scan the QR code to access the full paper. Yeah, thank you for your time. I'm happy to take questions.
Okay. Any questions? Perhaps I can ask one. So Filecoin's a little different from other blockchains that rely on computing resources to secure them, in that the computing resources it requires are not special purpose, right? It doesn't require ASICs or any such special purpose resource, but instead an adversary can draw on, for instance, cloud computing resources, storage, computation, so on and so forth. So how vulnerable do you think Filecoin is to attacks that involve rental of resources? Number one. Number two, do you have a sense of the cost of the equivalent of a 50% attack against Filecoin, the monetary cost?
Yeah, I think for the first question, I think rental, you need to rental a large amount of storage power in order to attack the protocol. I think currently Filecoin has a total storage capacity about like 11 EB, so that's quite a huge value. So I think it would be quite expensive, even just rent like 20% total storage power.
Yeah, do you have a ballpark figure on the monetary cost?
I don't have a number for that.
Sorry.
Has any of your security analysis involved any looking into like DRAND as the source of leadering in Filecoin? I guess that's a group of like 12 or 15 kind of socially incentivized folks. I was curious if anything has gone into incorporating that into the security analysis.
Yeah, so DRAND is a distributed randomness maintained by a group of participants, and most of them are independent of Filecoin. Like you can see all the participants. Can I project the screen?
That would have to be controlled back there, I think. Yeah, I don't think we're going to be able to do it quickly. So DRAND is kind of maintained by like 20 independent members of Filecoin, and it's quite stable. And I think Filecoin also has some plan to remove the need on DRAND to use some on-chain randomness.
I guess the follow-up was like, because they're externally incentivized, like I had wondered if any of the security like results at all, because I guess like the participation in each block is at some point based on like the random output from that. And so if that was gamed by people that are externally incentivized, if that would like feed into the analysis at all. But it sounds like that's already been considered in some sense.
Yeah, in this world, we assume that the DRAM is independent, and yeah, and yeah, it's an interesting topic to like introduce the attack space extending into the DRAM.
Thank you.
I think your analysis so far focused on the resilience. Do you see a way to extend it to analyze settlement time, latency?
Yeah, I think the proof technique we have so far only like give a asymptotic result on the security threshold, and I think for proof of stake protocol is quite like subtle to give like exact settlement time, and currently we are still using like the success probability of a certain attack to estimate the reasonable settlement time for the protocol.
Thanks.
Okay, let's thank Shuchao again. This concludes the session. We'll resume at 4 o'clock.